And I apologize if I pause here and there to let more people in, but welcome everybody to the Robert Ferguson Observatory Speaker Series. My name is Stephanie DeRomalar. I'm the volunteer coordinator for the observatory, and we're so thrilled and honored to have Dr. Thomas Greene presenting for us today, talking about the James Webb Telescope, of course, and I will introduce him in a moment. But before we start, I wanted to remind everybody to please keep yourselves on mute to minimize any background noise, obviously, and we'll open up for questions at the end. Possibly also, there might be some times in the middle that we'll open up for questions as well. You're also welcome to please post questions in the chat, and I'll monitor that and ask Dr. Greene to answer those once he's done with his presentation. So for those of you not familiar with us, the Robert Ferguson Observatory is run by the Valley of the Moon Observatory Association, which is a 501(c) nonprofit comprised of volunteer, amateur, and professional astronomers. RFO has fulfilled its mission of offering educational programs about science and astronomy for students, the public, and in support of educators for almost 25 years now. And the observatory is almost all volunteer run and typically, under normal circumstances, serves about 9,000 visitors annually. The observatory is located in beautiful Sugarloaf Ridge State Park and houses a 40-inch reflector telescope, the largest in Northern California that's accessible to the public, a robotic 20-inch research grade CCD scope, and an 8-inch 2-meter-long refractor scope. As the volunteer coordinator, I have to give a shameless plug for our robust volunteer program. And we have close to about 200 volunteers that work tirelessly to deliver programs to the public, offer public star parties and solar viewing events, provide classes and workshops, and manage all the behind the scenes tasks that it takes to keep the observatory running smoothly. Volunteering is a great way to get involved, and if that interests you, we have a volunteer application on our website, rfo.org, which you, if you fill out, will keep you informed of when we do our next new volunteer training. So to introduce Thomas Greene, Dr. Thomas Greene is an astrophysicist in the Space Science and Astrobiology Division at NASA Ames Research Center. He conducts observational studies of exoplanets and young stars and develops astronomical technologies and instrumentation. Dr. Greene is a co-investigator of the NIRCam and MIRI science instruments of the James Webb Space Telescope and serves on the JWST Users Committee. While at NASA Ames, he has served as the director of the Ames Center for Exoplanet Studies, project scientist of the SOFIA mission, and chief of the Astrophysics Branch. Before joining NASA, he worked at the Lockheed Martin Advanced Technology Center on NASA astrophysics missions. Prior to that, Dr. Greene was on the faculty of the University of Hawaii, where he was a support astronomer and later director of the NASA Infrared Telescope facility. He received his Ph.D. in astronomy from the University of Arizona and currently co-chairs the U.S. National Academies of Sciences Committee on Astronomy and Astrophysics and is a NASA representative on the Keck Observatory Science Steering Committee. And we're so thrilled to have his time today. So without further ado, I will pass it over to Dr. Greene.
Oh, thank you, Stephanie. And I'd like to thank everybody for turning out. I hear there's a good turnout, and I'm happy that you're all excited about hearing about James Webb. I'll do my best. So I think Stephanie went over all the info that's on the slide, and just like to say that I am definitely happy to be here tonight. So NASA has been launching telescopes into space for quite a while now. I think first ones were in the 60s. Also, other countries have sent telescopes into space. It takes a lot of effort, so why bother? So one major reason is because the atmosphere shields a lot of radiation, and that's a good thing for us on Earth, but it's not the greatest thing for learning about the universe. This shows 3 observatories that were part of the sequence called the Great Observatory starting in the 1990s. We have Hubble over here on the right. So it's still operating. It's operating mostly in the ultraviolet, visible, and near infrared. Chandra was launched in 1999. It's still operating. It's observing X-rays. And Spitzer was an infrared telescope that operated from 2003 to 2020. It was in an orbit that is now no longer accessible to us. So this sort of gave us a panchromatic view of the universe. And what can we see that is not in visible light? So I'll turn to the infrared because this is the wavelength regime that James Webb will use. This shows what scenes look like in visible light to our eyes, and this next one shows what things look like in the infrared. So we have these mammals, these meerkats, actually brighter in the infrared because they have internal heat. And we have a reptile here that has been in cold water, not very bright at all. So you see where cold-blooded comes from. So the body of this crocodile has cooled off from being in water before having the picture taken. This is a cartoon of the electromagnetic spectrum showing that visible light is crammed into a pretty small area here. So our eyes see from maybe like 450 nanometers to about 700 nanometers or so, about a factor of 2 in wavelength space. And that is only a small part of this whole spectrum. The electromagnetic spectrum starts at gamma rays and X-rays, ultraviolet, all filtered out by the atmosphere, thankfully. And visible gets through. Infrared, there's water and other molecules keeping out infrared. And radio waves do come through the atmosphere for the most part. And this shows where some observatories have focus. So Hubble has been sort of in this enhanced visible range, a little bit to the ultraviolet and to the infrared. James Webb is going to be in the red visible light all the way out to mid-infrared. And Spitzer was a pretty far infrared telescope there. So why would you want to point a telescope at something in infrared light? This shows some images of what some famous scenes in visible light. This was a famous Hubble Space Telescope image called Pillars of Creation in M16, I believe. You see that there are these big clouds here. There are these young bright stars. There's a lot of dust around that's scattering the starlight. And then this blue light, you're probably familiar with scattered light images. And you can't really see much into these clouds until you look in this infrared image here, and you start to see through the dust, and you can see some bright objects here that are not visible in the visible light. And then if you go to this mid-infrared light, you see that the dust itself is glowing because it's warm and it has some warmth. So different wavelengths allow you to see different things in the same scene. This is a little animation showing what a dark cloud looks like in visible light and where it's black, and then going through into infrared light, where you can start to see all these embedded young stars that are just not accessible otherwise. And without going into the infrared, you wouldn't actually be able to study the process of star formation because it's obscured by the dust of the young stars. And by the time the star is formed, then the dust is dissipated. So the dust sticks around for the whole process. A little comparison of the same object. So you probably recognize this is M51, right? The Whirlpool galaxy. And one interesting thing here is that in visible light, where things are dark in these dark lanes, things are bright in the infrared. And this is, again, being able to see the embedded objects in these dust lanes. So given that we've gotten this pretty unique capability, what science can we do with it? There, way back, we started working on hashing out science for this telescope quite a while ago. I joined actually in 1998, and it was like the first science working group where we're going to set out some basic science. And we figured that if the observatory could do this basic science in a number of different areas, it would be very capable and could do things that we hadn't thought of, because we knew that was probably going to be the most important science that it would do. So we sort of charted out 4 areas. The first one is seeing the first objects that lit up in the universe. And the next one was, how do galaxies evolve over time? We know what modern ones look like with the Milky Way and things like M51 that I just showed, things in the local group. And we don't have a great idea of the first objects that were formed and how they eventually turn into these nice, well-ordered spiral structures. Then we also want to understand more about this whole process of star and planet formation, sort of along the lines of that little animation you recently saw of being able to look into what's happening with some detail in the middle of dark clouds and also in the centers of the clouds where there are cores forming these stars and planets. And finally, studying planets in a little more detail, both ones in the solar system and ones elsewhere. We didn't really know much about ones elsewhere. They existed when we started, but we didn't know we could characterize them. But we'll be able to do that with James Webb. Let's talk about this first science topic, the first light and epoch of reionization of the universe. So the idea here is this is a time sequence with early times here, shortly after the Big Bang, to later times here. Actually, this is a little while after the Big Bang, because when the universe formed in the Big Bang, it was originally very hot, and it took a while for it to cool. But after it cooled to below 3,000 degrees or so, after say a few 100,000 years, that was cool enough to allow hydrogen atoms to form, and we didn't have just protons and electrons anymore. And then gravity eventually pulled those together and started to form stars, we believe. And the stars then lit up, and they started to reionize the universe, because the Big Bang was hot. That ionized the universe, which is basically just breaking the hydrogen atoms apart. And yes, the universe was initially almost all hydrogen and maybe about 10% helium, very little other elements. And then after some time, the stars evolved, and time goes on, their light goes out over some distance, dictated by the speed of light, and they develop these bubbles of ionization, and then the bubbles start to reconnect. And the key thing about these bubbles connecting is that if the atoms are ionized, then light can get out. So otherwise, the hydrogen atoms would absorb the light. We wouldn't be able to see back here. So at some point, we'll be able to see back to this kind of era in the universe, where we can see regions of young stars. Probably won't see stars themselves. We can see some of the first proto-galaxies that formed after the universe went through the Big Bang. Then, if we look deeply enough, we'll be able to see back in this time these first stars and first galaxies, and sort of superimposed on the same young early objects, we'll see more recent ones, because there are galaxies everywhere in the universe. So we sort of take a core sample of the universe just by looking at what we think there is nothing in deep space. Look out of the plane of the galaxy. You don't want the Milky Way to interfere with this. And this is something that Hubble has done on a number of studies. The Hubble Deep Field, I think, was the first one in the 1990s, and there have been ultra deep fields and whatnot. And we've got plans for doing this with Webb, where we'll be seeing a whole range of galaxies, from these fairly older and established ones like the Milky Way back to these younger ones. And in particular, we're sort of interested in this region here, where with a redshift about 3 we're sort of the peak of star formation. And the idea there is that once we start looking at that peak of star formation, this is a simulation of what one of these images is, with both the more well-established galaxies and also the younger, less organized ones. But by doing these deep samples, we could sort of start collecting stamps of these different galaxies in their different states of evolution, from the youngest, smallest proto-galaxies to these things starting to merge together, to developing spiral arm structures, to more established ones like this. And through observations and simulations, simulations are a big part of astrophysics these days. We try to put in a lot of the science that we know about radiation and gravity, so we can start to probe then how galaxies assemble themselves and how these different phases evolve. I also mentioned that we'd want to look at the birth of stars and planets. So we know now that when a star forms, it forms in a dense condensation in a cloud of dust and gas. And a disk forms first because there's some sort of stray rotation, regardless of what direction it is. And within one of these molecular clouds, you'll get, and these are not too dissimilar to looking in the summer Milky Way and seeing rifts and dark lanes. And within some of these clouds, like in Sagittarius, there are very dense regions that are starting to collapse gravitationally. We thought that disks existed, but we actually didn't really have good proof until the 1990s. So it seems like just when things contract because of conservation of angular momentum, everything isn't going to be able to fall on the star at once, because as the structure gets smaller, the angular velocity is going to speed up, and material will settle into a disk that gradually falls into the star. That was our idea, but it took Hubble images like this from the 1990s to actually prove to ourselves that disks existed. We know spectroscopically, we can measure some of that molecules in these disks are rotating under like Kepler's laws. And we see jets coming out of these that seem to be very closely linked to the infalling material. But we started to get exquisite images after the Hubble was repaired with its vision correcting optics in about 1995. And now we know they're commonplace. And lately they've been observed a lot with the ALMA radio telescope. Also want to know how stars live out their lives, how they die, and their impact on their media. So again, this is a picture of stars forming in a dusty cloud, and the infrared light allows us to see through there, and we can do a more complete census of stars. In fact, one of the programs I'm on, we're going to look in Orion, in the Flame Nebula, which you all may be familiar with, and there's an embedded population. In visible light, that's the part of the flame that's all dark, but in infrared light, we think we'll be able to count very low mass stars forming. We want to understand sort of what limits that lowest mass of star formation. Now, for planetary systems, this is an animation from the European Space Agency showing detection of planets. You may have seen this. So most planets have been discovered through this transit technique, where you're looking at a star, and if you're lucky, the orbit of the planet lines up. So it moves in front of the star, which is what it's doing now. And then down here is a plot of the brightness of the star, which was at this brightness before the planet got in front, and then it drops a little bit. It drops about 1% for a planet the size of Jupiter moving in front of a star like the sun. So that's not huge, but it's not terribly small. And to actually use that technique, though, to study the atmospheres, you have to look at much smaller changes. So that's something we're going to do with Webb. Now, when you use this transit technique to look at atmosphere, so it's same technique as showed in the previous slide, but what you're doing is you're really looking at the small bit of light that comes through the very edge of the atmospheres of the planets as they go in front of the star, because the planet is going to block the light, but its atmosphere will let a little bit through. And what we're looking for are signs of molecules that we have in the solar system. And these are pretty common molecules. We know they're in young stellar systems. We expect them to be in planets. So one common feature, and these are infrared spectra here. This is sort of like wavelengths from 5 to 20 microns. 5 microns, again, is about 10 times the wavelength of green light. And 20 microns, a few times that. So at 15 microns, there's a big feature in Earth's atmosphere due to carbon dioxide. Unfortunately, it's getting bigger as we dump more carbon dioxide in the atmosphere, and it's absorbing heat from the Earth. Now, it's also a pretty big feature in the terrestrial planets, other terrestrial planets in our solar system. Even though Mars doesn't have much of an atmosphere, it's got strong CO2 because the absorption is really strong per molecule. Now, Venus is really strong. You notice it's broader here. And Venus, and that's broadened by pressure. The pressure in Venus is maybe 100 times that of Earth. It's interesting, Mars is about 100 times less. So we're in the Goldilocks in terms of atmospheric pressure for life like us. And so we have some potential possibilities. And one thing that you can see if you look at these spectra, one thing you see on Earth, or a couple things you see on Earth that you don't see in others. One here is this ozone feature. This is actually a tracer of oxygen atoms and is an analog for the oxygen molecule for O2. Without plants going through photosynthesis, this may not be actually in Earth's atmosphere. There are other ways to get oxygen in atmospheres. Venus may have gone through this. If your oceans boil away, oxygen could be in the atmosphere for a while. So you have to be careful if you are saying whether these features really trace life or not, because they are both biotic and abiotic ways of producing features like this. And this one over here is due to water. So one spectrum like this will be very telling. So we're going to be doing this for a number of planets with James Webb. In particular, this system here is going to be a very fruitful place to look. This is the Trappist1 system. You may have heard about it. It's discovered with by the Belgians, believe it or not, with a telescope down in Chile. And it's only a half-meter telescope. This Trappist1 is a very red dwarf. It's like the lowest mass red dwarf without being a brown dwarf. It's like M8.5 or something. The system that it has many planets, so 7 planets. And they're all more or less the size of Earth. So this sort of shows the sizes of the planets on or density on this axis, which is kind of a proxy for size. And this shows how much radiation they get from their star, 1.0 being Earth. So you can see TRAPPIST-1D is almost as dense, almost as large as Earth, gets about the same amount of light. TRAPPIST-1B gets more light than Venus. C is pretty similar to Venus, etc. This is going to be a gold mine for searching for atmospheres of Earth-like planets because it's so close. It's only about 12 parsecs away. So that was kind of a whirlwind tour of some of the big science capabilities, and I'm happy to stop now to see if there are any questions on the science. If not, I'll go forward, but I'd be happy to entertain any questions on the science. Okay.
There aren't any in the chat.
Okay,
yet.
all right. So hearing none, I'll talk about what you as astronomers may be very interested in hearing about is the actual observatory and its similarities and differences from observatories we have here on Earth. Just a picture of what it looks like. I'll go through the various parts and why they are like they are. So every good telescope needs a mirror or a lens, right, to collect light. So it's got a 6.5 meter mirror. Secondary, there's a tertiary and there are instruments on the back. This is the baffle. It's a huge sunshade, and the way it operates is that Earth and Sun are always on one side, and this is the hot side. And then the telescope's always behind the shade, which allows it to cool off. It's important when you're observing an infrared light. As you saw, things with heat emit in the infrared. You don't want the telescope to emit more radiation than the objects that you're looking at. This is now an actual photo of the telescope itself. I think this was, this one here is at the Goddard Space Flight Center. This is the secondary is folded up. It's getting ready to be folded up for as it would be on launch. Here you see the side panels of the telescope are folded in also, and the secondary is up. And then these two, I think, are at Northrop Grumman, where it was integrated with the spacecraft. And here you see the telescope is on its, this is a deployable tower, and it's sitting over this sunshade. And the sunshade has 5 layers to allow heat to escape. And also it's some protection in case micrometeorites go through one layer of the sunshade. They go through all 5, given the angles that still shouldn't allow much scattered light through. This is a picture of how the size of the mirror compares to Hubble. So 6.5 meters is not small. It's not huge compared to Earth-based telescopes, but it's pretty big. So, and Hubble here is about 100 inches, 2.4 meters. To give you some idea, the last infrared telescope we had was Spitzer, and it was 0.85 meters. And it had to be smaller because it had to be cool, and it had a pretty limited budget as well. So you see that James Webb is going to have about 5 times the light gathering power in terms of area than Hubble did, and about 50 times that of Spitzer. Again, this sort of shows the two sides, the business side that does the observing, and the hot side that's got the spacecraft. There's a solar array here for power, the antenna for high gain communications with Earth. And there are these spreaders that come out and will spread it after launch. So the sunshade should be quite effective. So this warm side is going to be about the temperature of things around our distance from the sun, on the order of 300 Kelvin or so, a little warmer than room temperature. And the cold side, though, should allow the telescope itself to cool off to only about 40 degrees Kelvin. So that's 40 C above absolute zero. And it will take a while for that to happen. It'll take close to, I think, a month or so for it to get there, but it will get there. And parts of it will actually be operated colder. So the mirrors. As you know, again, you need mirrors to collect the light and bounce it around to the instruments and the detectors that you want to use with the telescope. The mirrors are all made out of beryllium, and they're coated with gold. Now, I'm sure that's also true for the Robert Ferguson Observatory, right? You've got your refractor is coated with gold,
right.
and yeah, right, and the lenses are made out of beryllium. So, what is this? Why? Well, I'll show you a little reason, but it takes a lot of energy to throw things into space, and they have to be light, is the bottom line for the weight. And gold is because we're working in the infrared, and gold has higher reflectivity. So it's more like 99% instead of the 98% of aluminum. And so, you know, what's the big deal isn't that 1 extra percent of reflectivity of the 99 versus 98, but it's the factor of 2 less in emissivity, which is the 1 minus reflectivity. So, so the emissivity of an aluminum mirror is like 2%. That means it's going to be emitting like a warm object with 2% efficiency. Anything that's not reflected is going to be emitted, and the gold brings that down to 1%. So that's in terms of producing an infrared background fog that can interfere with the observations. That's a big difference. This shows one of the mirror segments. I think these are 1.3 meters in diameter. The secondary mirror, tertiary. There's a fine steering mirror because the whole observatory is quite floppy, and so for fine guiding, we can't give corrections to the whole telescope for making like sub-arc second corrections, because it's it just can't respond too well. It's not stiff enough and it's not fast enough. So instead, we'll just be moving this little mirror. After we launch it and after it deploys, there's going to be about a month-long process of tuning up the mirror, because we saw that there are individual segments in the mirror. There are 18 individual segments. And if we're lucky, we'll get 18 individual images at start. We'll probably have to find some of the mirror segments. We'll turn on the camera. We'll see where the images are. So first, we have to look around, find all the segments find all the images from each segment, and then we move every segment a fine amount. There's motion controls on the individual segments, and we move them so that they all stack. And then this is this process here. You start to get the overlap in the point spread functions of each segment. And then not only do they have to all be on top of each other, then we need to phase the mirror. So we have to piston everything so that it all interferes and works as a single 6.5 meter mirror instead of 18 different 1.3 meter mirrors. And then we finally get a point spread function that's got the diffraction limited performance of a 6.5 meter mirror. And we've got a bunch of optics tools for this. First off, like I said, we're just going to hunt for segments with camera. And then we have these dispersed Hartmann sensors where we look at doing interferograms of the segment edges. And we got other tricks too for doing this phasing. We tried all this out on another segmented telescope you may have seen or heard about, the Keck Observatory in Hawaii. And this telescope has 36 segments in its mirror. There are two of them. You can see there's which one? I think this is Keck 2. That's Keck 1. And it's interesting to compare the two. This is a person here in the central hole of one of the Keck telescopes. That's probably Keck 1, sort of looking face on into the telescope. So James Webb's a little smaller than Keck. It's got about 1/3 of the area, 6.5 meters versus 10. Interesting how that adds up when you square things. James Webb is a faster telescope. We can only be so long because we need to fit in this fairing. The rocket fairings are only so big, and you don't want to make it too long too, because then there could be big moments of inertia and big torques. So f1.5 is pretty fast, but the whole telescope doesn't need to be f1.5 because we're figuring each segment separately. The wavelength of operation for James Webb, as I mentioned before, about 600 nanometers, 28 microns. Keck starts to work into the near ultraviolet, only goes out to about 5 microns. It could go longer, but again, the Earth's atmosphere doesn't cooperate well, and it's not really worthwhile. Then again, this is like the segment statistics. The Keck segments are a little bigger. They're 1.8 meters, but about the same size. Now, here's the segment weight. So 20 kilograms for one of these 1.3 meter beryllium segments versus 400 kilograms, and that is for a somewhat lightweighted 1.8 meter segment. So this adds up when you have 18 segments or when you have 36 segments. So this is why we're going to beryllium. The whole James Webb Observatory is only going to weigh 6.2 tons, and that's with all instruments. That's the telescope. That's with the spacecraft. That's with fuel. And in a comparison, Keck is about 270 tons, and that's just the weight on the azimuth bearing that turns with the telescope. The interesting thing is that when you're in space, you can operate pretty efficiently. So even though James Webb is a very expensive telescope, it only comes out to about 10 times more per hour than Keck over a 10-year lifetime. So I thought that was an interesting factoid. Some other pictures, some other eye candy for the telescope. This is it again assembled at the Goddard Space Flight Center. You can see both the complete primary, all 18 segments. By the way, there's 3 separate prescriptions in the primary mirror. There's the inner ring is one prescription, the outer ring is another, and then these edge ones that are kind of sticking out are other prescriptions, A, B, and C. And here is the secondary again, which goes down into this baffle tube. You can't see it now, but the instruments will bolt on to a structure in the back. This is the instruments in this integrated module. This is one of the instruments here that's covered in all this mylar. That's the European Space Agency's instruments, the facility spectrograph. It's called NIRSpec. This has got the cameras in it. This is NIRCam here. That's the near-infrared camera. And this is the mid-infrared instrument there. And this is another view of this instrument module. This is with it buttoned up, and this gets put onto the back of the telescope. And this is the telescope with the secondary folded in, the wings folded back, and the sunshade deployed, and it's on its tower there. So all this sunshade stuff has to fold up, right? And then that's what you can see here is with this purple stuff is the sunshade folded. The yellow is what's called ground support equipment. That's just holding the telescope here where we have gravity in allowing it to fold and unfold and get into these different configurations. This isn't going to launch with it, but the purple stuff will. And here we have the telescope in its launch configuration with technicians at Northrop Grumman. This ring here is the ring that we'll use to adapt to the rocket. And all of this here is the sunshade that'll fold down and fold out, and then you can see the mirror. And this part here is the spacecraft. A few words about the science instruments. This graph just sort of shows what wavelengths they work in, with short wavelengths and visible light over here, longer infrared wavelengths over here. And these letters are just sort of the bands from ground-based photometry. So most of the instruments are going to work in this range from red light from about 0.6 nanometers or 0.6 microns or 600 nanometers out to 5 microns. They use similar detector technologies. The instruments are both for imaging up here, spectroscopy down here. We've got 3 instruments that can work as cameras. The near-infrared camera, yes, pretty obvious. It also has spectroscopy modes. There's a mid-infrared instrument that has spectroscopy modes, and also this thing called NIRS, near-infrared slitless spectrograph, near-infrared imager and slitless spectrograph. And they've got multiple filters and some fancy stuff. NIRCam has coronagraphs over its wavelength range. You see MIRI does also, and NIRS has some coronagraphs as well. So you can look for faint objects near bright ones, like planets near stars. Then with spectroscopy, we've again, now all the instruments can do spectroscopy at some level or another. And this is most of the time in James Webb is going to be used for spectroscopy, because that's what we need to figure out what the constituent parts are of these objects that we're going to be observing and what molecules make them up. This shows the field of view of the instruments, again, on the whirlpool, just for some perspective here. So I think NIRSpec is about 3 arc minutes by 3 arc minutes. NIRCam has 2 fields of 2.2 by 2.2. MIRI is a little over 1 arc minute this way by almost 2 that way. And the NIRS field here, which is the same as NIRCam. NIRS has a lot of the same components as NIRCam. That's not how they're arranged on the sky, though. This is how they show up on the sky, with the center of the telescope being up here. This is sort of like the inner edge of the focal plane. NIRCam is closest to the center of the telescope because it's going to operate, it's going to be the prime imager. It's going to operate at the shortest wavelengths. We want it to have the best optical quality. And the whole telescope works, I should say, as a 3-mirror and a stigmat. It's not like a classical Cassegrain or Dald-Kirkham or you know, other observatories like that. It's meant to be good images over a wide field. These show the 2 fields of the NIRCam detectors, and they're split up like this because we have multiple detectors making up the fields. The coronagraph mid-infrared instrument is here with its coronagraphs. NIRS is here, showing its field of view a little over 2 arc minutes on the side, showing the spectra of objects that it can get. This shows the spectra that can be acquired with the NIRSpec instrument. And we also have a guider. So the guider is actually going to be in the focal plane, and it's part of this instrument. So we'll be using images acquired through the full telescope for guiding, just a little bit separated from the other instruments. Oh, and one thing I'll go back here. So this is about a 1/4 degree of scale of the distance between all the instruments. We'll be able to observe simultaneously with these different instruments. The big constraint there is just going to be bandwidth for getting data down. It's going to be far away. We can only bring down like about 1 megabit per second or something like that. So while you're taking images with NIRCam, you can be taking images with MIRI or spectra with NIRSpec. Some pictures of the instruments. This shows the near-infrared camera. Now, you might think you're looking, there's a mirror between the top and the bottom because they look sort of identical, right? This is the bench of NIRCam. If you looked closely, it says "Go Girl Scouts" on the edge. This is part of an outreach project with Girl Scouts. And we have 2 nearly identical modules, and they are indeed put back to back like this. And this is a highly redundant scenario. You saw on the previous slide, they have 2 fields of view that are right next to each other. And this is, again, going to be key for getting the telescope to work and a big imager. So we want to make sure that that it was very redundant and very unlikely to fail. The instrument was actually built in Palo Alto by the Lockheed Martin Advanced Technology Center, and the principal investigator is at the University of Arizona. And it uses 10 of these pretty high-tech detectors. These are 2K by 2K, which is smaller, I realize, than a lot of the CMOS detectors you probably have in your own telescopes, but they're really complicated. They have to have an infrared sensitive layer where every pixel is bonded to an amplifier circuit beneath it. So it's kind of like an infrared sensitive layer with every pixel bonded to every pixel of a CMOS detector there. And then this shows 4 of them all put together in a focal plane mosaic. is the near-infrared spectrograph. Again, it works at this wavelength range from 0.6 to 5 microns, has spectral resolution of several modes, and it has several different modes here. It'll be able to actually take spectra of multiple objects at the same time, which is pretty cool. It'll be able to open up little windows, these shutters, and be able to get spectra of multiple objects. Also, we'll be able to get spectra of single objects, these slits, and also be able to get a spectrum of a full region, a small region, 3 arc seconds by 3 arc seconds, a spectrum at every point. Now, NIRCam, as I mentioned, is made out of beryllium for its bench and some of its optics. NIRSpec is made out of this carbon silicon carbide material. Again, very low density, very lightweight. And this is a material that the Europeans have done very well with optics over the past 20 years. And this was contributed by the European Space Agency. And the picture here, it's a large instrument. These are its gratings and a grating wheel here. So you can see they're shiny, reflecting light. Then this is the near-infrared imager and the spectrograph. And it's kind of has a lot of the same mode as a NIRCam. So it's got the same plate scale as NIRCam in its coarse mode. And we'll also do the spectrum, and NIRCam will do too. It has one mode that's really well set up for doing planets. Mid-infrared instrument is under a lot more of this multi-layer insulation here because it has to be colder than the other instruments. The other instruments will be operating around 35 Kelvin or so, 35 C above absolute zero. MIRI's got to operate at about 6 or 7 Kelvin. And that's, again, because it works at longer infrared wavelengths. And particularly its detector has to be made cold so that its own radiation doesn't swamp the signals from astronomical objects. And this is a joint European-US effort. As part of this, and also part of NIRCam, the Europeans of the lion's share of this, they really designed a fantastic instrument. They built it. We supplied the detectors here in the US. And again, you see the picture of the telescope, and hopefully now more of these parts make sense as to what they are and why they are that way. Now, people all over the US and Europe developed James Webb, also Canada. So it's a project of Canadian Space Agency, the European Space Agency, and NASA. NASA is the major partner here. And people from all over the world, though, are going to, right now, has left North America, and it is here. It's in Kourou. This is the spaceport for the European Space Agency. I know some people in my teams that have gone down there. There's some tests last and did some basic electrical checkouts after it arrived there. With the rocket. So earlier, I tried to illustrate what science we thought Webb should be able to do. And this is a long time ago. And this shows a rough chart of what science people want to do with Webb now 20 some years later that people have proposed to use it. And this pie chart just kind of shows in different categories. So about 25% of the time is going to go to studying extrasolar planets, outside of the solar system, which we weren't sure it would do at all back in before the year 2000, 1998, when we were coming up with the first science ideas. Then about 25% for these two together are stars, stellar physics, individual stars, stellar populations, groups of stars, galaxies about a quarter. So that's kind of interesting breakdown. And this is just the way things fell out, equal quarter exoplanets, quarter stars, quarter galaxies, and then in the realm of compact objects, cosmology, etc., and then solar systems about 6%. This shows what it has to look like when it's in its fairing and how it's folded up. The fairing is only 5 meters in diameter. We have a 6.5 meter mirror, and there needs to be clearance because this thing is going to shake a lot when it launches, and you don't want it to bang up against the side of the fairing. Here is the deployment sequence for about the first 2 weeks after it launches. So Webb will never orbit the Earth. It does this direct injection trajectory, which I'll show you a little more in the next slide, but it leaves the Earth, separates from the rocket. Here we have the integrated observatory. The first thing that happens are these called unitized pallet structures fold out, and then this magic happens. These spreader bars will move out in the opposite direction, so the full sunshade will extend there, and then there's these bars here get turned to separate out the different layers. And also what's happening, I'll show you maybe in the next slide some other things are happening, but then the next steps are deploying the secondary, which we think should be pretty simple. It's just one mechanism for it to plop out the few hinges, and then deploying the wings of the mirror. And we'll have something that looks like a full telescope in about 2 weeks. This shows its path to where its final destination, which is not Earth. It's going to orbit at this point in the Sun-Earth system. It's the second Lagrangian point, with the Sun here, the Earth here, and it's out here. The Moon's about here. It's about 4 times further away from Earth than the Moon is. So it's about 1 million miles away, 1.6 million kilometers. And it just turns out this is a stable point in the Sun-Earth system. It's not intuitive. You can imagine there's a stable point where the gravity, right, between Sun and Earth balance. If you move a little bit of the distance, like 1% of the distance, towards the Sun from Earth, then the poles of the gravity balance, that's called L1. And there are a number of observatories there, mostly ones observing the Sun and ones observing the Earth. When we get this coronal mass ejection notices, they're from often observatories at this L1 location. And we have some, there's at least one observatory there looking at whole disk images of Earth, because the weather satellites aren't high enough to see the full hemisphere of the Earth at once. 30 minutes after launch is when the vehicle separates, and solar array deploys almost immediately after that. We deploy the antenna to start talking to it, and then you start going through this the sunshade. So this is like at about 3 days afterwards when the sunshade pallet structures deploy, etc., and whatnot. And then it takes about a month for it to settle into this orbit around the L2 point. There are some other observatories at the Sun-Earth L2. There's some other astrophysics observatories there. Planck, which studied the microwave background, Herschel, I think some more. Just some closing words here about how will everybody benefit from Webb. So try to illustrate some science, but in just the broader question of why is something like this worth doing? So I think it's going to address questions that people have asked for thousands of years, and it's been recorded since the Greeks. People have been asking, what's in the universe? How old is it? How do we get here? Are we alone? And I hopefully illustrated some of that through the science, how some of the first galaxies are going to answer this question about what's in the universe, watching how they evolved. So it'll help us answer the question, how we got here. We'll see how stars and planets form and die. And we'll learn about how planets around other stars are like and unlike Earth, and if their atmospheres show any signs of life. Also, in a more practical realm, it has helped us advance our scientific technology. People around the world, or at least around North America and Europe, have been involved in building it. And there are over 1,000 people involved in this, and it's brought us together from all these different countries. And hopefully its science will bring together many more people from around the world, just like Hubble has and other space images have, as we look at the results and we ponder our connections with the universe. So that's what I have, and I'm happy to take any questions.
Thank you so much. What a
thank you. Awesome.
So fascinating, and especially being at this global project, if you will. We do have a bunch of questions, so I will go ahead and read some of these off in no particular order. How much imaging is available to watch all of the parts of the telescope unfold?
Well, we're not super high tech that way. We don't have cameras like you see on these SpaceX launch videos and all that. There might be, I think there may be cameras on the Ariane rocket, but we don't have any on the telescope itself. So we're going to have to rely on telemetry from the sensors. So we'll be a little bit blind, but we'll have other senses. We'll be able to see from magnetic sensors and whatnot about how things are in position.
Great, great. One question is, will the moon perturb the L2 orbital state?
Well, I was sort of wondering, you think you might run into trouble if you launch close to full moon. But I think that the answer is basically no. The moon's pretty far away. The answer is yes and no. I mean, it has to perturb it a little bit, but it turns out that L2 isn't that stable for a number of reasons, and we'll have to orbit around L2. So, and that's going to require some station keeping. It's not like a really stable position anyway. And that's a good point. The moon and its orbit could be part of what's perturbing things at L2. I'll have to ask about that. I'll have to see if I can find some dynamicists.
Perfect. What propulsion engines are used to stabilize and orient the spacecraft?
Yeah, so it's going to burn hydrazine fuel like a lot of spacecraft do. We are hoping to be able, so we're going to completely fill the tanks. The good news is that the observatory came in a little bit underweight, so that's going to allow us to completely fill the tanks. And if we get a good injection into L2, so the telescope and the whole observatory is going to be on its own fuel starting 30 minutes after launch, and it's going to have to make all these mid-course corrections on its own fuel. And if those go well, if they don't require longer burns, we hope to get about 14 years of operations out of it. And that's going to be operating around orbiting L2, making corrections there. We'll actually do the pointing by moving these wheels. We have these wheels, these reaction wheels that spin, right? And just using conservation of angular momentum, if you spin a wheel one way, the thing that it's attached to is going to want to go the other way. And that's how we do pointing. But at some point, you get the wheels spinning as fast as they can. And you have to unload that spin, and then you have to fire these thrusters in an opposite direction to unload the spin on the wheels.
Oh, thank you. Why was the ESA launch site chosen over USA, as a scope has to be shipped there from here?
Yeah, boy, that was a tough one. That is just what NASA and the European Space Agency worked out for their contributions. It would have been, so when you work with a partnership with an agency like this, you want to have contributions be pretty discrete things that are easy to separate and integrate. So instruments were an obvious one. They're doing 2.5 instruments. Europeans are doing 2.5 instruments. Launch was another thing, because then the whole observatory can get attached to the launch vehicle. It gets trickier if you're saying, well, you designed this part and we designed that part. And then it gets more difficult because of, I don't know, different design rules, different conventions, different working hours, et cetera. It's just less separable and it's harder to integrate. The US launch agencies, the US launch companies did not like that. And it took a few years to get that sorted out, but everybody is good with that. Also, the Ariane 5 is a big rocket, and I think maybe an Atlas of some sort could do Webb, but for example, this is too big to go up on something like a Falcon 9 that we have now.
Mm-hmm. Okay. Are deep field images planned for James Webb?
Oh yeah, good question. So the near-infrared camera team that I'm on is going to be doing 400 hours of deep field images. That's in the first year. That's just one of the teams, and there's going to be a similar amount done, so of the same fields, but with spectroscopy. So and in those 400 hours, they'll be doing some tiling of an area, but also going very deep. They expect to detect about 100,000 different galaxies in those deep fields. So this will be tremendously deeper than what has been done with Hubble.
Wow, amazing. Sorry, I've been through the questions here. I understand that the orbit of the Webb telescope will be quite high. What challenges and or limitations will this present?
Well, no user serviceable parts inside. You know, you've seen those stickers on consumer electronics. Well, we might as well stick one on here because we have no way of getting there. And if we did get there, just being there would probably contaminate it because we've got that whole telescope thing going on. And just getting close to it, you open the door to an airlock, air is going to come out, it's going to freeze on the mirrors, the water in the air is going to freeze on the mirrors and absorb. So that I think is the biggest downside of going to this really nice stable location. You know, it's great. We'll be able to observe almost 24/7. The only kind of limited by spacecraft activities, very different from Hubble, which is in like this 300-mile high-ish Earth orbit, 550 kilometers. The Hubble gets interrupted by day and night. There are all these gravitational torques on it. It's not a very stable, temperature changes. This is going to be much more stable, but the downside of that is once it goes there, it's there, and it's not coming back.
Right, right. Can't be serviced, right?
Yeah.
Why can't James Webb see blue light?
Our detectors just aren't that sensitive. We only go down to this 600 nanometer limit. Going to, there are also some problems going to shorter wavelengths. One, Hubble has done a really good job, right, with shorter wavelengths. So we didn't really see the pressing need of going there. It also gets a lot harder to figure the mirrors with good, with lower wavefront error. Right now, we think we're going to be diffraction limited around 1 to 2 microns. And if you want to go to like blue light, you'd want to be able to push those mirrors. And the problem about that isn't just figuring the mirrors, is like we have to figure the mirrors at room temperature, and they get operated at 40 Kelvin, and then they move there. And we've done a lot of testing. I've got slides showing them going all around the country and through all these different test things, and they're in test chambers. And it would have been really hard. And also for the instruments where all the optics have to get figured at room temperature and then operated cold. So it just makes things a lot harder to get to the diffraction limit at shorter wavelengths.
Got it. Got it. This was an earlier question, and I think may have already been answered in your presentation, but I'll ask it anyway. Are there any interesting planetary nebula observations to be made?
Well, yeah, I saw that, and the answer is yes. I'm not sure what all the science goals are, but one of the things we're going to do, and one of the things I did on the near-infrared cameras, I developed the spectroscopy mode, and we're going to use Planetary Nebula to calibrate the wavelengths. So it's one of the, we've got 6 months of checkout. Something I didn't mention is after we launch. And so we'll be going through, and a month of that is going to be tuning up the telescope, right? Getting all the images right. But we're going through all the instruments, all their modes, and we're going to be using Planetary Nebula because they have all these nice oxygen and other emission lines to then use them as calibrators for tuning up wavelengths. So that's the one thing I know about for Planetary Nebula. And you can actually look at this whole science program. It's online if you search for James Webb Telescope approved science programs, and they're kind of in different categories.
Okay. Yeah, I was wondering, actually, I know you had said it takes about a month to fine tune the mirrors, and one of the earlier people we talked to from NASA had said that the first images, I think, weren't coming out until maybe May, June, that they would be coming back. So I was wondering about that long lead time. Yeah,
there's going to be a lot of pressure. We've been telling some on the users committee, telling NASA, you know, people don't want to know how this thing is working. So there's a blog, and they aim to update it about weekly. It already exists, and I could maybe dig around for the URL, but or you just search for Webb Space Telescope blog, and hoping to put in updates. So for example, I think they will put in updates every few days for the first few weeks about how the deployments are going. And they'll say, this is successful, and then you can like look at that chart that I showed and see if they skipped any. And if they, so maybe those weren't as successful as others, or they need to be retried or something like that. So hopefully that they will update that. I hope, and I think they've kind of mentioned that maybe they'll send out an image once the whole telescope is phased. So maybe a couple months in after the telescope has gotten to L2 for a month, another month phasing the telescope, we get a nice image. Hopefully they'll be able to release that. And then other things as we go on and check out different modes. Maybe NASA usually does this set of science observations called early release observations. They'll pick a few things of scientific targets that are also kind of illustrate the power of the observatory and have a big media conference. And those will probably be done, at the end of commissioning. So if this launches as planned on December 18th, then that will be probably, those images and those data will probably be taken in early June.
Oh, exciting. We do have a couple more questions. Do you still, I know it's about 8. Do you still have time to answer?
Sure.
Okay. Let's see. Where is, where's control for the telescope on Earth? Goddard?
No, it's actually, it's near Goddard. It's at the Space Telescope Science Institute in Baltimore. I've been spending a lot of time there, and I'm gonna be spending more time. I just got some of my assignments today, so I'm gonna be going out during that 6-month commissioning period. It's like about 10 trips of 5 days each. We've got a big missions operation control room there with rooms for the spacecraft, the instruments, optics rooms, whatnot, and there's a backup facility at Goddard, but that institute is actually operating the Hubble now, and they're also mostly though the interface, the gate for the science community. So that's where people propose for the observations. They'll actually host the data and make the data available. They put it through the pipeline, so it's kind of all together there in Baltimore. It's on the Johns Hopkins campus.
Okay. Let's see, how will the launch of the Webb telescope affect the use and function of the Hubble telescope?
We want them to be operated simultaneously for as long as possible. Hubble is getting up there. It's, if it was one of us, it'd probably be collecting Social Security by now. And I'm not sure if it's out of safe mode. It's been in safe mode since I think the end of October. With some of the instruments. I think this one isn't as bad of an anomaly as what happened last summer. So, but we really want to have contemporary observations. We hope to have some observing programs where objects can be observed simultaneously or nearly simultaneously with both.
Okay. Would a near equatorial launch make more sense than a mid-latitude?
Yeah, and that's one nice thing about the spaceport, the French spaceport in Kourou, is that it's really close to the equator, much closer than Florida is. So it's using the rotational velocity of the Earth to kind of maximize the velocity of the spacecraft.
Got it. Somebody asked long exposures long exposures or stacked short ones.
Yeah, good question. So we're limited to roughly 1,000-second exposures by cosmic rays. Once, because we're going to be outside of the Earth's magnetic field, they're going to have cosmic rays, mostly high energy protons and alpha particles from the sun, and from also from black holes and whatnot, active galaxies, at a rate such that in about 1,000 seconds, we've got about a 20% hit rate over a detector. And that's what's going to limit the exposure times. Now, brighter objects will saturate earlier than that. But, like, for example, some of these transits, we're looking at pretty bright stars. And some of these individual observations, we're looking for small things in bright stars. We try to observe as long as we can without filling up the well of the detector. And in some cases, that's only seconds. And we'll be doing many of those. And some of these, we're not going to stack them, but we'll actually look at the whole time series and look for changes between them, depending on what the science is.
Okay. Let's see. Is the renaming of the telescope a dynamic discussion going forward?
Yeah, so there's been some controversy about the name. A number of people were concerned about the name being associated with James Webb, who was second at the State Department at a time during the Lavender Scare, when there was some expulsion of gays and lesbians from the federal service. NASA did some research into that. They had their own internal historian. They hired other people. They went through various archives. They couldn't trace Webb to any particular actions associated with this. He is associated with some actions in NASA that promoted equity among African Americans in the NASA service. Some of this has been documented elsewhere. So they've decided to not change the name.
I didn't even know about that. Learning from these questions myself. I believe that those were all the questions in the chat. I hope I didn't miss any. You know, people are welcome to unmute themselves if there are any other questions. Do so now. I think we're a little after 8, so I want to respect your time, Dr. Greene, but any other questions before we log off? And we had several thank yous and amazing, thank you very much on the chat as well. I wanted to relay that too.
And I'd like to say you're welcome and thank you for attending. I think it's really great that you're interested. There's, the launch is going to be December 18th. Let's see, I think I've got a slide here for the URL, but basically just Google for like Webb Space Telescope launch. So it's going to be on NASA TV. There's a website here. There are mission countdown timers, etc. We'll see when it actually launches, but it's scheduled to launch around 4:20 a.m. Pacific time on December 18th. The launch windows are about an hour or two, and but it can launch, I think, any day. So hopefully it'll go off on the 18th, if not the 19th or 20th, and then let's see how it goes. And
I could have sworn that
please check it out.
I could have sworn a few weeks ago I thought it was the 20th or 21st. I thought that it was planning to launch in December, but am I mistaken on that, or did they?
No, it's really the 18th. It's been the 18th for a while. The originally we're sort of hoping to do it on Halloween, but got delayed a bit by a few various things. So it is the 18th, and then you can go to Google for a Webb countdown timer, and it'll tell you how many days.
Oh, exciting. Well, we will be watching that for sure. Well, thank you so much. And like I said, I hope you see in the chat several people saying thank you and very interesting presentation. And thank you for your time and insights, and so appreciated. We're super excited. And Chris, did you have any final words at the end here as well?
Certainly. Well, Tom, thank you so much. It was fantastic. If you can lend RFO, your graphic designer, for your awesome graphics, I'm all ears.
I stole them all.
And I'd also like to mention that RFO has a docents and programs committee and an active board and a couple hundred docents, and we are going to be following the activities of the launch and the science and the mission, and we will be discerning what other kinds of public programs we can do to share with the public as the mission progresses. So keep your eyes and ears open. Those in attendance, we will put notices on our website. I may send you an email. We're very interested in this. We're likely to target 8, 12, and potential venues for sharing this information. It's just hard to say, but we are exceptionally interested and appreciative of your talk and your time. Thank you very much.
You're welcome. And I hope to be able to share some results early on in the mission after it's commissioned, and it'd be great to be able to come up and do that in public. I always, in person, I always enjoy visiting Kentwood and would love to see your observatory.
Awesome.
That would be fantastic. Well, thank you so much. And thank you everybody for attending. So appreciated. And hopefully we will see you all again very soon under the stars.
Good.
Thank you.
Bye.
Thank you. Bye-bye.